Gnanam Paramam Dheyam. Knowledge is supreme.
Let me recall that in the last lecture we have seen examples of non-algebraically closed fields, and we have also stated fundamental theorem of algebra which says that the field of complex numbers is algebraically closed and the proof is pending. When I have enough prerequisites, I will come back to the proof of this. That is one thing. Next thing is, today I am going to introduce what are called algebraic extensions. And study their basic properties. And to do this, also I will need some concepts from elementary abstract algebra which are concerning rings, ring homomorphisms, ideals, prime ideals, etc. So all these concepts I will briefly recall with some guiding examples. So this should keep us going a little faster in a pace, and also we will reach the subject with more relevant prerequisites. So as you know that we are studying polynomials over a field, and especially their zeros or their roots, and we have seen that the zeros of a given polynomial with a coefficients in a given field that may not lie in the field K, or only some of them can lie in the field K and all of them may not lie in the field K. So we want to extend our given base field to a larger field so that the given polynomial has all zeros in that bigger field. This is our main aim now, and then we want to see how minimally we can do that and study these field extensions. Those are precisely what are called Galois extensions of the polynomial f. So let me slowly start recalling. Suppose when we have a polynomial f, so before I go on to the polynomials, I briefly recall what is a ring homomorphism. Ring homomorphisms, I think I had briefly recalled earlier also, but let us do it once again. So when you have two rings R and S, they are rings. And let me remind you, when I say rings, by definition they are commutative rings with unity. Unity means multiplicative identity. That means it's a neutral element for the multiplicative monoid of R, multiplicative monoid of S. So ring homomorphism is a map phi from R to S such that it satisfies three properties. One, it should respect the addition. That means it should be when you think it is a map from R plus to S plus, it should be a group homomorphism. So this is a group homomorphism. And when you restrict, when you think it is a map from a monoid, multiplicative monoid of R to multiplicative monoid of S, this should be a monoid homomorphism. And let me stress, monoid homomorphism has two requirements, that it respects the multiplication, that is one. So that is phi of x times y equal to phi x times phi y. And again I have mentioned earlier also this xy is a product in R and this Cx Cy is a product in S. So though we are writing it in the same, it is understood that when we write like this, first we are taking the product in R and then taking its image, and this means first taking the images and then multiplying in S. These two results are same. So that is first property of the monoid homomorphism. Another one is phi of identity 1R should go to 1S. Normally many books they don't assume this, but I will assume in this course that it satisfies this property and it is very important. And I don't again the group homomorphism, just that whether you add and take the image or you take the images and add, this result is same. So such a map between the ring is called a ring homomorphisms. And now we want to see some examples of ring homomorphisms. So some examples, and usually examples should consist our rings which we want to study. For example, so examples. One, take the ring Z and take R any other ring. See, this is any other ring, any ring, and Z is our ring of integers. And so I want to give a ring homomorphism from Z to R. So that means I should map N to somewhere and check that it satisfies the properties of the ring homomorphism. But you see, also remember that when we want to give a ring homomorphism, that we need to map one of the ring Z to one of the ring R. That means we have no choice. One, usual one, this is usual one, it should go to one R. And once one goes to one R, then this N has no choice, because this N, when it is positive, you think it is 1 plus 1 plus 1 n times. When it is negative, you think it is minus 1 times minus n times. So this N you should think 1 plus 1 plus 1 n times when n is positive, and minus 1 plus minus 1 minus n times if n is negative. Of course, when n is 0, we know we need a group homomorphism from Z plus to R plus, so 0 has to go to 0. So 0 has to go to 0, and then I know it should respect the addition. That means when I know where 1 goes, this is clearly has to go to n times 1 R, because it should respect the addition, and this will automatically go to minus n times 1 R. So in every time n has to go to n times 1 R. That is what we conclude. So that means there is exactly one ring homomorphism from Z to R. There is a unique, so I will write the result. There is a unique ring homomorphism from Z into any other ring R. And this unique homomorphism, it depends on R, because it tells where 1 goes to R. So which is denoted by chi of R. So chi of R is a ring homomorphism, the unique one from Z to R. This is very important fact, and I will keep using this again and again. Okay, so this is one prime example what we will keep looking, and the next example is then many other examples I want to give together. So second example, let us take K to be any field, Actually, assuming field is not really necessary. We could do, or more generally, K to be any commutative ring. But when we apply, we are going to apply many things to the fields only. But there is no harm in knowing the general definition. So then we consider a polynomial ring from this field K. We have constructed the polynomial ring whose elements are precisely the polynomials. And I want to give R is any ring, R is any arbitrary ring, and I want to give a ring homomorphism from here to here. So, whenever I have an element small x in R, I am going to give a ring homomorphism corresponding to this small x. So, therefore, I am going to denote it by phi of small x, not phi, sorry, E of small x. I am going to define a map E of small x. So, how do I define it? Take any polynomial f. This is a0 plus a1x plus an xn. Any polynomial looks like this. And this I want to map it to somebody in R. And I know only x in R. And I know these AIs, they are fixed. When I fix f, then I want to map this somewhere. So, I want to try whether this makes sense. A0 plus a1 small x plus an small x power n. And this should be again an element in R. So, naturally we should put a condition on R, not arbitrary, but it should have multiplication of K inside that. There should be a scalar multiplication of K on R. So, we need to assume, in order this to make sense, we need to assume that R is what is called a K algebra. What is K algebra? K algebra is where there is a multiplication also and there is a scalar multiplication also. So, I want to elaborate this and then come back to this example. And then we will have many more examples of this kind. This is very important. So, let us now recall what is a K algebra. So now we have a base ring K. K is, I will call it base field. One could take also ring, commutative ring or commutative ring, but commutative is very important. And we have a ring R. R is a ring, or better to write it, a definition. A ring R which, just to remember, R has a two binary operation, addition and multiplication, and they satisfy the usual properties of the ring, both these binary operations. A ring R is called a K algebra if there exists a scalar multiplication one should think a map from K cross R to R. This is usually denoted by scalars are the elements of K and these elements of R are denoted by small x. This should go somewhere which is an element of R again, and that is denoted by AX. This is a scalar multiplication. This is called a scalar multiplication of K on R, which is a map like this, which satisfies the compatibility properties. Compatibility properties, what are they? They are the following properties. That simply means that this scalar multiplication shouldn't be compatible with this given multiplication of the ring R. This is a given multiplication of the ring R. So multiplication, one should again think it's a map from R cross R to R, which is associative, etc., etc. So what are the compatibility properties of the scalar multiplication of K? So first of all, with the plus. So first one is with the addition of the ring, it should be compatible. That means if I take this R with plus this abelian group, this is a K vector space. That means whether you add first and multiply by scalar, or you multiply by scalars and add, this result is same. So that I will just simply write it, A times x plus y equal to ax plus ay. Also if I add in the field K, so that is a plus b times x should be ax plus by, bx. This is for all a, b in K and for all x, y in R. And one more, 1 times x should be x. This 1 is now 1 in K. So these are the compatibility properties, so that it becomes a vector space. One more thing I should write it really, that is multiplication in K, that is a times b and times x, this should be same as a times bx. So these four properties which satisfies the scalar multiplication which satisfies these four properties, that will make this abelian group R plus as a K vector space. And when you are dealing with not with the field case but with the commutative ring case, then one, instead of vector space, one uses the word K moduli. Properties are the same. So when one says the K vector space, that indicates the base ring you are assuming is a field. Otherwise, it may not be field, it's a commutative ring in general. So this is the compatibility of the scalar multiplication with this plus, and obviously the addition and multiplication of the given field. The second one, now with the multiplication of the ring. These are the compatibility with the multiplication of the ring. Now I will write the multiplication in the ring by just dot. So that means what? Whether I multiply first in the scalar, so that means if I have a, b are in the scalars and x, y are elements in the ring R, then whether I multiply this scalar by this x, resulting element is in R, and this scalar with this element by, I get two elements in R, and I multiply these elements in the ring. This result should be, first I multiply these a and b in the field K, and then multiply these elements in the ring x and y, and then multiply this as a scalar multiplication. So this result should be same. Then one says that this scalar multiplication of K on R is compatible with the ring multiplication of the ring. So typical example is the polynomial algebra. So this is called an algebra. So let's see some examples. 6 examples. 1, K field, and then this Kx is the polynomial ring. then Kx is a K algebra. With scalar multiplication A times any f to be, you multiply all coefficients of A by f by A. So this is A naught plus A1 x etc etc plus an x power n, where f is A0 plus A1 x plus an x power n. This is how the scalar multiplication of k on kx is given. So I should have said this example before, it doesn't matter. If R is any ring, then R is a Z algebra in a unique way. There is only one scalar multiplication with the scalar multiplication. So we need a map from Z cross R to R. So this is obviously given. Take any n, take any x and map it to nx. Nx is clear. Nx is n x plus x n times when n is positive, and otherwise it is minus x plus minus x minus n times when n is negative. So this is the only one scalar multiplication which makes R as a Z module. Okay, one more. This is what we will use it more often. 7. Third one. If I have K is a field contained in a bigger field L. So these are fields. So this is a bigger field, and when I say K is a subfield of L or L is a bigger field than K, that means we assume that the operations of K are induced from the operations of L, or one says operations in L are extended from the operations of K. So such a thing is called a field extension. If they need not be field also. If K is a ring and L is a ring, then we say if K is a subring of L, then we will say ring extension. Then the bigger one, so let us stick to the field extension case because that is what we are going to use more often. L is a bigger field than L. So typical example of this kind are Q contained in R or R contained in C or Q contained in C. These are the typical examples of this kind. And that is what one of our requirement today, that I want to extend the field so that the given polynomial has zeros in a bigger field. All zeros in fact. I want to extend the field in such a way that a given polynomial in K, X has all zeros in the bigger field. It may not have zeros in L. So in any case, when you have such a field extension, then the upper one, L, is a K algebra. So remember, to give a K algebra, you need a ring, which already L is a ring. In fact, L is a field. And so in this case also it's fine. So L is a ring, and you need a scalar multiplication of K on L. But then you can just restrict that multiplication of L. So take any A in K and take any X in L and map it to AX as if you are multiplying these elements are in L, because the multiplication in the ring here is same as whether you take and consider them as elements here or elements of K. So this is a scalar multiplication, and with this scalar multiplication this L becomes a K algebra. Okay, now one more example, I will just say it. So a ring can be a ring R can be K algebra in many ways. We will see these kind of examples when in the assignments. So this means the scalar multiplication of the ring of K on the ring R may be different. Okay, so we have seen now ring homomorphisms, we have seen K algebras. One more important class of K algebra I want to give is, before I go on to that, I also want to recall what should be a K algebra homomorphism. K algebra homomorphism, this should mean a ring homomorphism and K vector space homomorphism, K linear. So what does that mean? Let me write in the notation now. Now we have two K algebras R and S and a map between them phi. So R and S are K algebras and phi is a map between them. It is called a K algebra homomorphism. If it satisfies, first of all, phi should be ring homomorphism. And now we know that because they are K algebras, they are K vector spaces, and therefore it makes sense to talk about K vector space homomorphisms or K linear map. That means phi should satisfy this property K Ax plus By equal to A phi x plus B phi y for all A B in K and xy in R. Such a thing is called a K algebra homomorphism. So any ring homomorphism is a Z algebra homomorphism. So example, because there you don't have to check nothing, there is only one. So any ring homomorphism is a Z algebra homomorphism. This is immediate from the definitions. So recall that what we have done in this few minutes is we have recalled a definition of ring homomorphism. We have also defined what are K algebras, and we have also defined what is the K algebra homomorphisms. And in the next, after the break, I will continue with more examples which should lead to the concept of algebraic elements. We will continue after the break. Thank you.